As we begin our lesson on real numbers, I want to start by referring back to the term set. So you would have already learned about sets in prior math classes. And so sets can be anything from the students in this class to sets of numbers like we're going to discuss in this lesson. I'm actually going to work up so that you can see how these numbers fit into the other sets. The first set of numbers is at the very bottom that we're going to talk about, and these are natural numbers or counting numbers. These are the numbers that you would have learned when you were first learning numbers 1, 2, 3, and 4. From that, we add just the number 0, and that is our set of whole numbers. Now you'll notice that whole numbers do not have negatives because that is our next set, which is our integers. Integers are whole numbers and their opposites. And the set above that, which is our rational numbers, throws in our fractions. Now, all of those are considered real numbers. They are in the real number set. But you'll notice that you have this one outlier over here, which are irrational numbers. And these are numbers that cannot be written as a fraction. As decimals, the decimals do not terminate and they do not repeat. You'll also notice that each of these sets have a little shorthand or a symbol that represents them. Most of them look like the first letter. In this case, real numbers are real. Now you'll notice that these are different. Q stands for rational numbers, and Q with this little prime mark is irrational. I is also an accepted shorthand for irrational numbers, which is why your integer set is represented by Z. Then you have whole numbers represented by that W, natural numbers represented by that N. Very often see these number sets is in a Venn diagram, and this is a good representation of how they fit into each other. The large outside set is your real numbers. You'll notice you have rational over here, irrational rather, over here. And then you have your natural, which is inside your whole, inside your integer, inside your rational. And so if I were to give examples of these, your natural would be 1, 2, 3, and so on. Whole includes that 0. An example of an integer would be a negative number. An example of a rational would be a fraction. And an example of an irrational would be a radical that does not have a perfect root or a very familiar pi. And we are used to actual number sets and ways to represent them. We have used a number line many, many times at this point. And then thermometers are another way to represent numbers in a set, as well as devices that measure things like snowfall or rainfall. So let's get into the specific definitions of these number sets. A rational number can be represented as a ratio of integers. Its decimal form will terminate or repeat. And so any number that can be written as a fraction or as a decimal, and that decimal ends, or it could be written as a fraction and you have a decimal that repeats, or it could simply be a number. Remember, that can be written as a fraction. Those are your rational numbers. An irrational number, however, cannot be represented as a ratio of integers, and its decimal form does not terminate or repeat. And so, as I mentioned, pi is one of the more famous ones, but you will often see patterns. And while that looks like you have repeating, you don't, because that is a repeating pattern, but it is not a repeating number. And so if you saw something like this, that would be irrational. And then any of your square roots that don't have perfect roots fall into that irrational set as well. So let's look at some properties of your real numbers. Your community property states that A plus B equals B plus A. All this means in both addition or multiplication, A times B equals B times A, is that if you have all addition or all multiplication, your order does not matter. Your associative property tells you that if you have all addition or all multiplication, you can group them however you want, and that also will not affect your answer. The identity property for addition states that if you add 0 to any number, it does not affect the identity of the number. So A plus 0 equals A, or 0 plus A equals A. The identity property for multiplication is basically the same, but of course you are multiplying by 1 when you don't change the identity. The inverse property for addition says that if you add any number to its inverse, you're going to get 0. And multiplication, if you multiply any number by its multiplicative inverse, also called its reciprocal, then you will always equal 1. The distributive property of multiplication is that if you have a number that is multiplied by a group that is either added or subtracted, you can distribute it through. It is repeated multiplication, so A times B plus A times C. So let's determine which properties are being used here. We have 8x plus 5y equals 5y plus 8x. This is indicating that the order does not matter, so this is commutative property of addition. For the next one, we have 3b times 1 over 3b equals 1. This is its inverse, multiplicative inverse. So this is the multiplicative inverse property. For this last one, we have 5xyz plus 0 equals 5xyz. The 0 did not change the identity. So this is the additive identity property. 5 times 2 times pi equals 10 pi. Very often people think this is distributive, but remember distributive has to have a plus or minus in here. And so this is just the associative property because all they did was change the grouping. They grouped the 5 and the 2 to make it the 10. And this last one, we have negative 3x times parentheses 2x minus y. And they've changed that to negative 6x squared plus 3xy. This is distribution. They've taken this and distributed it through. So this is the distributive property. The last term we're going to look at is the term closed. A set is closed under an operation if the result of performing that operation on members of the set always results in a member of the set. What does that mean? Well, that means if you look at an operation, addition, subtraction, multiplication, division, will you always get the number set you're talking about if you start in that number set? So for example, natural numbers. Well, if I take any two natural numbers and add them, I will get a natural number. So yes, it is closed for addition. But let's look at subtraction. If I take any two natural numbers and subtract them, -1 is not a natural number. Natural numbers are only 1, 2, 3, 4, 5, and they don't include negatives. So it is not closed for subtraction. If I look at multiplication, if I multiply any two natural numbers, I will get a natural number. So it is closed for multiplication. However, with division, 2 divided by 3, that is a rational number, not natural, and so it is not closed for division. And so if you can give just one example where it is not does not fall within that set, then it is not closed for that particular operation.